lesson. Okay, so you're supposed to have done some homework on your own. I hope you have done that. So I've gone through checkpoint 7 review, whereby we try to identify the parents that form the salt. Then from there, right, we know that the dominant gene will determine the nature of the salt form. Then from there, we deduce whether this is an acidic salt or basic salt. Okay, then we derive the calculation part. Okay, so this is what you have done, should have done as homework. Okay, so let's quickly look at work example 8. For work example 8, you are asked to calculate the pH of a salt. Okay, so I hope you can recognize that this is a salt. And we know that the anion comes from the acid, while the cation comes from the base. So fully soluble salt will undergo full dissociation to form your conjugate base and your cation. Okay, so remember, the salt that we are looking at is always fully soluble, so we'll show full dissociation, after which we have to find out whether this salt can undergo alkaline hydrolysis or acidic hydrolysis. Okay, so with this, right, we all should recognize that the weak acid is the one that forms the anion. Okay, so the anion comes from the weak acid, correct, as told to you here in this work example. Then the sodium plus comes from a strong base, the sodium hydroxide. So overall, strong base will be the one that causes the anion here that undergo hydrolysis. Now remember, strong base, weak acid produces a basic salt. Okay, so basic salt means that OH minus will be released. So OH minus release must come from your anion, A minus. Okay, so during this proton transfer, OH minus will be released. Since it's OH minus, you use Kb expression. Okay, so this is something that you need to associate with. When OH minus is released, the extent of this hydrolysis will be measured by Kb. When H plus is released, the extent of this hydrolysis will be measured by Ka. Okay, so whether it's Ka or Kb, you look at what is released, OH minus or H plus. So OH minus release, extent of reaction is by your Kb. Okay, but if you look at the information provided by the question, you are not given Kb. Instead, you are given Ka. Okay, so with this in mind, right, you need to recall that Ka multiplied by Kb of a conjugate acid-base pair, what is their relationship? Yeah, conjugate acid-base pair, right? They will be equate to conjugate acid-base pair. Okay, so they will be equals to Kw. So therefore, I can arrive at the value of Kb by making use of this relationship. Okay, then I do a square root. I can calculate my pOH first, followed by my pH. Okay, so this is what is shown or demonstrated by this work example 8. Can? All right, so this work example 8 is just the salt, nothing else. Okay, so let's look at the next work example. In the next work example 9, okay, this one is more complicated because you are not just given a salt. Instead, you are forming a salt. Okay, so what do I mean by forming a salt? Okay, so if you look at this very carefully, you are mixing the weak base and the strong acid. Okay, so with this, the parent is already told to you. So when they form a salt, in this case, right, using the ICF table. Okay, so you are familiar with ICE, whereby you are working with an equilibrium system. Okay, so this is the concentration at equilibrium. So what is ICF is what is the final component in this mixture. And this final component comes from a reaction. Okay, so I need you to understand that there is a reaction between the weak base and the strong acid over here, and it's represented by an irreversible arrow. Okay, so in this acid-base reaction is an irreversible process. A weak base and a strong acid. Okay, so it has to be an irreversible process. Okay, then I need you to also appreciate that your two solutions, when added together, they are 25 cm³ each. So total volume now becomes 50 cm³. So addition of two solutions you have to consider dilution. Okay, this is what we have learned last lesson also. When you add two solutions together, you have to consider dilution. Okay, so from the number of moles of the weak base and the strong acid, you know that it will be a complete neutralization. Okay, so in the final reaction mixture, none in excess, all converted to salt. Okay, so in other words, you are looking at a salt solution, nothing else. Okay, so just a salt solution. We know that this is an acidic salt. Therefore, my cation will be the one that undergo hydrolysis, and H plus will be released as a result. Okay, acidic salt, H plus is released. Therefore, the extent of this hydrolysis is measured by Ka, as mentioned. All right, so since Ka is already given, there's no further manipulation required by you. Okay, then you can just do a square root and can calculate the pH value. Straightforward. Okay, so something to note is there is a reaction. Okay, so you need to ask yourself, when you mix two solutions together, is there any reaction? And this reaction will be represented by a complete arrow. Complete arrow. Okay, then you use an ICF table to find what is the final component. Is it a salt solution or is there unreacted acid or base? Okay, then after which you consider only hydrolysis, but do appreciate that the concentration of the salt has become diluted, is halved because of doubling of the volume, total volume double. Can? All right, so this is what we are going to look at. So this is the summary of what you are supposed to deduce from the two-word example. So as demonstrated from the two-word example, when you work with an acidic salt or basic salt, okay, so remember, they come from fully soluble salt. Can you help me change that phrasing? Because it's very confusing. Salt undergo full dissociation. All right, but they are weak acid and weak base. Therefore, they will dissociate to give H plus and OH minus partially. All right, so in this context, this looks very confusing. Can you help me change that? Okay, so the salt will undergo full dissociation, but as a weak acid or weak base, they will partially dissociate to give H plus and OH minus. Okay, so do you know why we are allowed to use square root? So this is not unfamiliar to you. This is the square root that we have used when we calculate pH of a weak acid as well as a weak base. Okay, so why is it applicable in this situation as well? So I need you to see that for acidic salt or base, okay, you see that there is equal concentration of the products formed. So when my anion undergo hydrolysis, there will be equal concentration of OH minus and HA produced. If my cation undergo hydrolysis, right, it will be equal concentration of the weak base and the H plus released. So as a result, because they are equal, then I can do a square root. That's the relationship because it's an x squared, right? So to solve for x, it will be a square root. And also, we do the assumption as well. We assume that the concentration of A minus and the ammonium cation, conjugate acid, at equilibrium is approximately the same as the initial. Okay, this is what we have assumed also when we calculate pH of a weak acid and weak base. Same thing. Okay, so in other words, what we have over here is initial because the extent of dissociation is very small. Therefore, we can assume it to be negligible. Okay, so we are allowed to make certain assumptions because it's a good approximation and it simplifies your calculation. Okay. Any question at this point of time? No question, huh? So when this is 0.001, this will be a plus 0.001 plus 0.001, right? So if the initial concentration is 0.1 to start with, then 0.1 minus 0.001 is approximately the same as 0.1. That's why we can do this approximation. But then if you look at the numerator, 0.001 squared is 10 minus 6. It's not a negligible change. Huh? Okay, so when I talk about it being negligible, it's only applicable if we are making a difference, taking a difference of value. Okay, so when I subtract a minus 0.001 from 0.1, it's a negligible change. But when I multiply small values together, it's a significant change. Because some of you ask me, hey, why is it that I assume this, but I don't assume this to be negligible? Then everything is negligible, there's nothing to calculate. Agree with me? Can or not? All right, so when you multiply two small numbers together, there is a significant change. But when you carry out a subtraction, there is negligible change. This is math. And all right, so let's move on to the next part. Okay, so I hope you have done this already. I'll just show you the answer. You should have thought through. So I won't go through the fundamentals with you anymore. So what's the answer to this part? D. Is it D? What? Canada. It should be Canada. Okay, so why you choose D? Now remember, this one is a weak acid. This comes from a strong base. So the salt is a basic salt. Well, this is neutral, pH 7. So your second solution, pH should be higher. Huh? No, basic salt means that it must be more than 7. pH more than 7. This one is neutral, pH equals to 7. So the answer should be Canada. All of you got Canada? Yeah, so if your friend didn't get Canada, then maybe you can try to explain to your friend. Okay, if not, then I assume you are okay. All right, the next part, how do we calculate the pH over here? So first of all, can you tell me which part of ammonium sulfate will undergo hydrolysis? There must be hydrolysis. If there's no hydrolysis, there's nothing to calculate. It's just pH 7. Correct or not? Okay, so recognize that this is a salt. Definitely a salt. Then it comes from, who are the parents? Who is the parent that formed this ammonium sulfate? Who's the parent? Who's the parent? Parent. The base and the acid that form this salt. Yeah, the ammonia. Ammonia is a weak base. Sulfate is sulfuric acid. Sulfuric acid, what is the nature of the acid? Yeah, it's a strong acid. So you end up with a acidic salt. So if it's an acidic salt, who will undergo hydrolysis? Yeah, the ammonium cation. Acidic salt means that it's going to release H+, right? So H+ must come from your ammonium salt. Okay, so remember, it will undergo partial dissociation. Okay, so it will be measured by Ka expression. Okay, so are you given Ka value? You're not given Ka value, you're given Kb. So how do you get a Ka value? Yeah, Kw, 10 minus 14 divided by your Kb value. Then you get your Ka value. Okay, is there anything else that you need to pay attention to? So is my concentration of ammonium cation 0.1 mole per dm cube? No, you should know that the ammonium sulfate upon full dissociation, remember, the salt always undergoes full dissociation when placed in water. So there will be 2 moles of ammonium cation and 1 mole of sulfate anion released. Okay, so starting with 0.1, then this will become 0.2 mole per dm cube. Okay, so when I substitute my Ka expression, it will be square root of concentration of your salt multiplied by its Ka value. So this concentration must be 0.2. So if you did not manage to get this answer, it could be you have forgotten to multiply by 2. Can? Okay, you just double check your working. If everything agrees with mine, then you should get the correct answer. Can or not? Which statement? Oh, this one is your thinking process. Yeah, you don't need to write. So this one, right, most probably is just 1 mark. Yeah, so 1 mark you just calculate. But before you can even start calculation, you must go through the thinking process. Okay? Can? Any other question about this part? Okay, so this marking here, the points allocated is likely to be 1 or 2 mark only. Okay? It's not a lot. So you have to do your thinking process fast. Okay, so anyone who is not able to find the answer, can or not? So there are 2 things. You need to calculate your Ka value and you need to consider 0.2. Okay, any question? No question, then I move on. Answer 4.98. Sign, what sign? pH, there's no units because it's a logarithm function. Okay, let's move on. So what is a buffer solution? Okay, so please take note, there are 2 types of buffer, and if you look at the definition given to you, you must have a weak acid and its conjugate base. Okay, so the conjugate base will be in the form of a salt. Okay, then if it's a weak base and its conjugate acid, then this is in the form of the salt. So this will be an acidic buffer. A weak acid and the salt will form an acidic buffer. A weak base and the salt will form a basic buffer. Okay, so no matter what, right, there must be a weak acid or weak base, okay, as a component of your buffer. Okay, so very quickly, right, let's look at this 1, 2, 3 mixture. Okay, so which of the following are buffers? Which of the following are buffer? Two and three. Why 2 and 3? Okay, number 1 is not a buffer. Why so? Yeah, because this is a strong acid. Right? Strong acid, don't even need to see whether there's salt or not. Definitely not a buffer. Okay, then how about this one? It's also a strong acid. Nitric acid is a strong acid. Nitrous acid is a weak acid. Sulfuric acid is a strong acid. Sulfurous acid is a weak acid. This one you have to memorize. Okay, nobody can help you. So you need to recognize this straight away. Okay, so this is a strong acid. Then whether there's salt or not doesn't matter. It will not be able to form any buffer. Okay, how about the last one? Last one, is it a buffer? Yes, it is a buffer because you have a lone pair on the nitrogen. Is essentially a weak base. Okay, and this is the salt. Right? How do I know that this is the salt? Because I add 1 H plus. This is what I'll get as the cation. So this is the conjugate acid of my weak base. This is the salt. So what kind of buffer have I formed here? Acidic buffer or basic buffer? Basic buffer. And what does basic buffer mean? It maintains pH above 7. It will keep the pH value constant at above 7. And what is this specific value? It depends on the ratio of your weak base and the salt. Okay, so basic buffer means that it tries to maintain pH above 7 at a certain value. Can? Right, so let's move on. How does a buffer work? Okay, so I need you to help me highlight this part. A buffer must have a large reservoir. So earlier part, we learned that a buffer must have a weak acid or weak base. But there's now an additional criteria. It must have a large reservoir of the conjugate acid-base pair. The salt and the weak acid, the salt and the weak base must be in large reservoir. Okay, and I need you to help me change this part. Acidic buffer is formed by mixing your weak acid and your salt. You have to mix them together. Okay, so this is the salt. We undergo full dissociation. This is your weak acid, partial ionization to form H+. Okay, these two are added together to form this acidic buffer. Okay, now what do I mean by large reservoir? What does it mean? 1000 mole per dm cube is large reservoir? Must it be 1000 mole per dm cube? Does that mean that? Okay, so my next question is, right, how do you think a buffer will differ from a weak acid or weak base in terms of composition? How do you think? Will there be any difference? So if you look at the weak acid, when it undergoes partial dissociation, we see that if I subtract X, then this will be formed X is to X, 1 is to 1, right? So this is what we will observe if this solution only consists of a weak acid. Okay, so in this case, is this large reservoir of the weak acid conjugate acid base pair? Is this considered as a large reservoir? No. So what happens over here is, what do we do here? We have to add salt. Okay, so I need you to see that there will be a additional salt added to this system. Okay, so it will increase your A- concentration. That's how we create a large reservoir. Okay, and I also need you to see that when I add sodium salt to this system, is it going to affect the equilibrium? When I add salt to this system, is it going to affect the POE of the weak acid? Yes, it does. Okay, so addition of the soluble salt will cause a surplus of your A-. And according to the Chatelier principle, it will favor the POE backwards. Okay, so what does it mean? What does it mean? With the addition of your salt, this will drop according to the Chatelier principle in response to the sudden increase in A-. Okay, so I need you to see that the H+ concentration will drop by a little bit in the presence of your conjugate base. Okay, so please take note, the H+ do not drop to 0. It's just getting smaller, but it's not a 0 value because it's an equilibrium. Equilibrium means that it cannot become 0. Can? Yep.
So the NAA is large.
Yeah, so the sodium salt will be the large reservoir of the conjugate base. It's the source of the conjugate base. Okay, so whatever that I've just told you, right, is being described in this paragraph. Here, the sodium salt is fully dissociated. It will produce a surplus of the A-, which will suppress the dissociation of your weak acid. Okay, can? So whatever that I've just discussed with you, right, is described in this paragraph. Okay? Yeah, diagram.
So then shouldn't NAA be higher?
Huh? Na+, but Na+ doesn't do anything. Yeah, the sodium plus concentration is higher, yes, but it doesn't do anything to your system. Yeah, it's higher because this is added as a pair. Sodium plus and A- added together as a salt. Yeah, so your sodium plus will increase, but it doesn't do anything to your system.
So it's just an excess.
Yeah. Okay, so in other words, right, in summary, this is what is going to happen. Once we don't have H+ equals to A-, we form an acidic buffer. Once OH- is not equal to the concentration of the conjugate acid, then we form a buffer. Okay? Originally, they are equal if it's just weak acid or weak base. Okay, but now they are no longer equal. Once they are no longer equal, they become a buffer. Very important, this part. Okay, once you cause the imbalance of the H plus and the A minus.
What do you mean by salt slash orange base?
Yeah, so sometimes we refer to A minus as a salt, but it's also a conjugate base of the weak acid.
So you're labeling A minus.
Yeah, so this one is to describe this part. They are the same. Yeah. Okay, so this is actually to differentiate a weak acid and an acidic buffer. If it's a weak acid, H plus and A minus are definitely equal. Okay, you only created a buffer when the H plus and the A minus are no longer equal. Okay, that's what I'm trying to tell you here. You must be very clear, because later on when you do calculation, you must know what are you looking at. Is it a buffer or is it just a weak acid? Very important. If you cannot differentiate, right, then it will affect how you calculate. Okay? Any question about this part? Okay, if no, right, then I'll just proceed. Okay, so this is what you're supposed to see. Okay, so sometimes A-level question will ask you, can you demonstrate your understanding of buffering action of a buffer through the use of an equation? Okay, so the equation is, please take note, is a irreversible sign. Okay, because it's a base acid reaction. It's an acid-base reaction. Okay, so it will be an irreversible sign. Why is it completely removed? Why is it completely removed? It's because you have a large reservoir of the conjugate base. Because of this large reservoir, it will enable a complete removal. Okay, so if you write this, it will be marked wrong, even though the rest are all correct. Okay, all right, so when you show that, when you write an equation to show buffering action, you have to show a complete removal. Okay, so same thing. You have a large reservoir of the acid. Therefore, it will completely remove the small amount of OH minus released. Okay, so the small amount of OH minus added, right, it will be completely removed by the large reservoir of the weak acid. Can? All right, so two keywords must be small amount of H plus or OH minus. There must be a large reservoir of the conjugate acid base pair. Okay, later on I will emphasize to you why must it be a small amount. Okay, let's look at checkpoint 9. So checkpoint 9 is what you have done, you're supposed to have done already. So I just quickly show you the answer. So this is your conjugate acid base pair, the weak base, and its conjugate acid. Okay, so please take note, the H plus has to be removed by your weak base, while the OH minus has to be removed by your acid, conjugate acid. Okay, basically it's just acid-base reaction. Okay, so this one, this is what you're going to see, right? So remember to show complete removal. Once you write reversible arrow, 0 straight away. Okay, so again, we emphasize small amount, large reservoir. Small amount, large reservoir. Can? So far, so good? Hmm? Yep. Yeah, so it can only resist changes. That means the change is negligible, but it doesn't mean that it's unchanged. Pardon again? Yeah, completely gone. Okay, so later on, I'm going to show you an expression. And that expression will explain to you why even after complete removal, there is still a slight change to the pH. Okay, so you just bear with me again, a little while. Right, so let's move on to the next part. Okay, so how do we calculate pH of a buffer? Okay, so this is the part. All right, so let's look at page 30. So remember, the acidic buffer is formed in the presence of a weak acid and the salt added together. Okay, so remember, this is what we have used as my expression or so-called shortcut when we are dealing with pH of acidic salt or pH of a weak acid. We just do square root, right? Okay, and the reason why we can just do square root is we know that the weak acid or the acidic salt, the weak base and the basic salt, they give you equal concentration of the product. That's why you are allowed to do a shortcut to do a square root. Okay, but for a buffer system, are they still equal? For a buffer system, are they still equal? No. For a buffer system, I will have extra of the salt added. This is extra. Yeah, while this will drop by a little bit, according to Le Chatelier principle. To form an acidic buffer, I will add this extra part. All right, while this will drop by a little bit. The weak acid will be suppressed. Okay, so once this occurs, the concentration of H plus and A minus are no longer equal. So of course, when these two are no longer equal, I can no longer use this to calculate my pH. Agree? Okay, so this is what is going to happen. I can still use my Ka expression for acidic buffer, but I'm going to rearrange my expression to become as such. Okay, so because they are no longer equal, then this becomes a fraction. Okay, so the concentration of the weak acid and the concentration of the salt is a fraction and is a component in calculation of your pH. Okay, so when you do a negative log on both sides, this is what you're going to derive at. And we give this special equation a special name. It's called a Henderson blah, blah, blah equation. Okay, you go and pronounce yourself. All right, so in other words, right, it means what? A pH depends on two things. Number one, the Ka value. Okay, the pH of a buffer depends on Ka value as well as the ratio of your salt to your weak acid concentration. Okay, so these two will affect. Then of course, at a given temperature, Ka value doesn't change that, right? At a given temperature, Ka remains constant. But then do appreciate that this ratio will change. Okay, so how will this ratio change? Okay, so if you can recall, right, on page 29 of your notes. Oh, okay, never mind. I think I put it later. Okay, so this is what is derived from here. So we are going to use this expression to calculate our pH. So if you look at work example 10, okay, let's go through it together. So for example 10, you have your weak base, ammonia, and your salt added together, the conjugate acid. Okay, and they are not equal volume. It's not, it need not always be equal volume. You see that it's a proportion of 20 to 30. Okay, so you see that the total volume has become 50. By proportion, this will be the new concentration of your weak base and its salt or conjugate acid. Okay, so this is after dilution. You have to consider dilution. Okay, then you substitute into the expression to calculate the pH. Okay, so this is what is demonstrated in your work example. So with this in mind, right, can you try checkpoint 10 now and see whether you are able to get the answer? Okay, you should recognize that this is a weak acid and it's salt. So the pH value should be less than 7 because it's an acidic buffer. Okay, weak acid and its salt will form an acidic buffer. So pH is expected to be less than 7. Okay, so therefore you should calculate pH using the Ka value. Right, so with this in mind, this is what it will look like. Okay, so actually the calculation is very straightforward because you notice that the weak acid and the salt, they are equal concentration. They are equal in concentration. So logarithm 1 is essentially 0. So this whole part, right, will become 0. Therefore, it will just be a negative log of your Ka value. Okay, okay, so let's move on. Oh, this part. Okay, I would like you to try this. This is not in your checkpoint, but this is tutorial. All right, so I need to show you how to calculate if this appears in your tutorial. Okay, so instead of just adding the weak acid and the salt together, or weak base and the salt together, we are forming a buffer system through a reaction. Okay, so in this case, you need to calculate the ICF. Okay, so when these two are added together, you should expect a reaction. So how do you write the reaction that represents the reaction between your weak acid and your strong base? Okay, so you need to find out, does it undergo complete neutralization or is it going to be partial neutralized? When it's partial neutralized, what type of reaction mixture have you created here? Okay, can you try? ICF, not E. Yeah, because it's not equilibrium.
So it reacts.
Yeah, it reacts. So the reaction is acid-base reaction. Your weak acid will lose a proton, while your strong base will gain a proton to form water. So it's a complete arrow. This will be the salt that is formed, then your water. So it's a proton transfer to form water. Okay, so what is the initial amount of your weak acid? Initial amount of your weak acid will be 0.04 multiplied by 0.1, right? That is the initial amount of your weak acid. Then initial amount of your strong base, 0.01 times 0.1. This is 0 and 0 to start with. Okay, so what is the change? So you notice that something is in excess, right? Who is in excess? The weak acid in excess. So the sodium hydroxide, which is limiting, will be completely reacted away. Agree? The one that is limiting will be completely used up, right? So this will be the same amount of weak acid used up as well. Agree? They react 1:1, right? Then this will be how much of the salt that is formed. Then of course this one don't need to care lah. Water equals medium, negligible change. Okay, then after that you calculate how much is left behind. So how much of the weak acid is left behind? How much of the weak acid is left behind? 0.003. This one, 0, no more. Okay, then this one is 0.001. So what do we have over here? What kind of system are we looking at? It's an acidic buffer. Okay, acidic buffer because we have the weak acid together with its conjugate base, acidic buffer. So if it's an acidic buffer, what expression do I use to calculate its pH? pH equals to pKa plus logarithm of your salt. Salt is 0.001, but your weak acid 0.003. Okay. Oh, no need to convert the concentration because they are swimming in the same total volume of 50 cm3. If you want to convert the concentration, also can. Don't convert, also can, because they will cancel each other out anyway, right? In this fraction. Okay, so that will be the ratio of the salt over weak acid. So what's your answer? So what's your answer? My answer is 5.22. Do you have 5.22? Wrong? Huh? 4.74. Why? pH. Huh? Oh, I put it wrongly here. Okay, so what's the answer? 4.27. Okay, do you have 4.27? Okay, so what do you learn from here? You learn that there are two ways to increase the concentration of the salt. One way will be just throw in the salt. Okay, the second way will be through the use of acid-base equilibrium, acid-base reaction to push the weak acid dissociation forward. Okay, there are two ways. One way will be just add the salt. Second way will be through the use of acid-base reaction.
So Ka is always 1%.
Ka for this acid lah. Okay, of course, we are assuming that temperature is constant at 25 degrees Celsius. So this one is a constant value, constant.
For every other acid, 25 degrees Celsius.
Every acid will have their own unique Ka value. Yeah. So the Ka value will change for different acid. So do you need me to explain the second part? How the second part works? Can apply Le Chatelier principle, huh? So when you have your hydroxide added to the system, right? This will undergo acid-base reaction to form water. Okay, so during that reaction, it will reduce the concentration of H plus. So when it reduces concentration of H plus, POE will respond. So how does POE respond? When the H plus is being used up by your alkali, how does the POE respond? It will move forward. So POE will move forward. Huh? So in this case, this will increase. This will increase. As the POE of the weak acid move forward, the concentration of the salt will increase. Okay, while this one is partially offset. Remember, Le Chatelier principle, to partially offset the change. So the drop in H plus will be partially offset. Okay? So you can see for yourself that these two concentrations, they are no longer equal. Can see that these two concentrations, they are no longer equal. Once they are no longer equal, they are buffer. Remember this? Yeah. Okay, so this is what we have learned over here. So buffer capacity, right? For buffer to be more resistant towards changes in pH, concentration of your acid and base should be large. Okay, and what do I mean by large? Later on, I'm going to explain. So maximum buffer capacity is when these ratios are equals to 1. Okay, the buffer capacity is the best when the ratio of the salt and the weak acid, salt and the weak base are 1. Okay, so why do we emphasize small amount of H plus? Remember on page 29, right? We always emphasize small amount of H plus. So what do I mean by this? Okay, so let's say, right, I've added small amount. So if my conjugate base is 0.1, my small amount of H plus will be 1% of it. It will be 0.001. And it will be completely reacted away, right? So this, when it's completely reacted away, this will be subtracted by 0.001. Agree? Agree or not? Then this will be plus 0.001. Agree? All right. Now, if we go back to the fraction, if my conjugate acid-base pair, the starting point is 0.1, then this one must also be 0.1. Because we say that maximum buffer is 1, right? The ratio of the salt and the weak acid must be equals to 1. So if this is 0.1, this must also be 0.1 for it to operate at maximum buffer capacity. Agree? Yeah. So notice that this ratio will then be adjusted. Okay, what do I mean by this? When your small amount of H plus that is removed by your A minus, then this will drop to become 0.009. Am I right? Yeah, your A minus becomes this, right? After reaction. Then wrong. What is it? What is the value? 0.99. A minus will become 0.099. Yeah, while your HA, right, will become 0.101. Okay, notice that this and this has undergone change, but it's only 1% change. Is negligible. So the ratio is almost the same as before, but there is a change. Yeah, therefore the pH value change, but the change in the pH value is negligible. So it's not going to stay constant. Because just now you asked me, right? If it's completely removed, why would the pH value change? Yeah, this is the reason why. Because the fraction changes. Yeah, okay. So of course, if you add in 0.1 here, then there will be a drastic change. Then that's no longer a buffer. Okay, that's why we always emphasize that small amount, large reservoir. Okay, and the small amount and the large reservoir is relative. Small amount is 1% of the original conjugate acid-base pair concentration. You get me? That's the meaning of small amount. It's just 1%. Okay, so it will give you a negligible change. No, because I'm trying to demonstrate the importance of small amount, large reservoir. Yeah, small amount means what? Only a small percentage of it. Yeah. Can? Does it make sense? I mean, I'm trying to use math. Can? Okay, so in this case, right, please take note, your buffer capacity of having 1,000 each versus 10 mole and 10 mole each will be different. Because 1% of this is 10 mole of H plus. 1% of this is 0.1 mole of H plus, correct? Okay, so when your large reservoir becomes much larger, then the amount of H plus it can buffer will be larger as well, proportionately. Do I make sense? Okay, all right, the rest you can self-read. Then let's quickly look at checkpoint 11. Checkpoint 11? Oh, already 9 o'clock. So can you take checkpoint 11 as homework? Okay, so the next time I see you, I'll go through checkpoint 11. Then we will have the prelude to the titration calculation. Yeah, okay, Ken? Right, that's all for today. Is this too complicated? Or should I just ask you to memorize and calculate? That's all. Huh? Don't memorize. Oh, okay. Okay, anyway, some of the tutorial questions require you to show this understanding. Yeah. So some of the tutorial question is relevant to this. Sometimes students, what they do is they just memorize and apply. So I don't know what's your style, because sometimes when you know more, you're even more confused.